Hey everyone, and welcome to this explainer. I am absolutely thrilled to have you here today. So, we're going to tackle a topic that honestly sounds pretty intimidating at first, but is actually incredibly fascinating once you break it down. We are demystifying real-time audio programming in Python. If you're the kind of focused learner who loves taking raw concepts and actually building something functional with them, well, you are definitely in the right place. Let's turn your computer into a live audio processing powerhouse. This right here is the ultimate question, isn't it? I mean, when you speak into a microphone, you expect to hear the results instantly. But the second you introduce your own code into the middle of that path, you're immediately up against two massive enemies: latency and complexity. Latency is that super frustrating delay where you speak and then the sound echoes back a half second later. It's the worst. And complexity? That's the dizzying array of sample rates, buffers, and all that dense digital signal processing math. Honestly, it's enough to make you want to throw in the towel. But don't worry, we're going to look at the exact Python libraries that act as the ultimate solution to this puzzle, giving you the power to process audio smoothly and efficiently. Okay, let's dive into this. Section 1, Audio I/O, moving the sound. Before we can do any fancy math, we really need to understand the pipes, how we actually get audio into our machine from the microphone and then back out to the speakers. To move this sound around, the Python ecosystem essentially gives us two distinct vehicles: PyAudio and SoundDevice. Think of this exactly like choosing between a manual and an automatic transmission in a car. PyAudio is our manual transmission. It's a very low-level interface to port audio, and it gives you this incredible fine-grained control over your audio streams. It's highly respected, super well-established in the community. But because it's a manual transmission, it's definitely got a steep learning curve. You need to intimately understand audio concepts like sampling rates and buffer sizes to drive it without stalling. On the flip side, we have SoundDevice. This is your modern automatic transmission. It offers a much higher level abstraction than PyAudio, making it exceptionally user-friendly and incredibly fast for beginners to get started with. It automatically supports a wide range of audio backends right out of the box. The trade-off, though, is that it might not offer quite that same level of deep, fine-grained control if you're trying to execute highly complex DSP scenarios. Moving right along to Section 2, DSP, crunching the numbers. So we figured out how to pipe the audio, but actually, scratch that. Moving sound is not the same as processing sound. Let's transition from merely moving the sound to actually manipulating it inside our Python workshop. What's really interesting here is that our Audio I/O libraries, they don't actually process the data. PyAudio and SoundDevice basically just hand you a digital bucket of raw sound. To actually process it, to manipulate the pitch, change the volume, or add an effect, you absolutely need NumPy. NumPy is the mathematical heavyweight of the Python world. It is a powerful numerical library that is literally essential for DSP, or digital signal processing tasks. It gives us highly efficient array operations, which means it can process thousands of audio samples in a fraction of a second. It handles all the essential mathematical functions, and the beautiful part is it integrates seamlessly with whatever I/O library you chose, whether that was PyAudio or SoundDevice. Now, if NumPy is your standard toolkit, SciPy is the advanced heavy machinery you bring in for the really big jobs. SciPy literally builds upon NumPy to offer highly specialized signal processing tools. If you want to build an equalizer, you're going to need filters. If you want to analyze the frequency spectrum of a sound, you'll need fast Fourier transforms or FFTs. Well, SciPy has all of this built in, ready to go. Now, I want to be super clear here. This is an optional upgrade. If your project just requires basic functionality, like simply turning the volume up or down, NumPy is all you need. But if you want to get into serious audio analysis, SciPy simplifies those complex, common DSP tasks immensely. Section 3. Choosing your ideal stack. We've met the players, now it's time to draft your team. Depending on your specific experience level and what you want your project to do, you need to choose the right combination of these tools. Let's break down this final library selection. If you're an experienced user, or you're building something that demands absolute, precise control over how the audio hardware behaves, PyAudio is for sure your go-to. If you're a beginner, or your main priority is getting a working prototype running quickly without getting bogged down in low-level audio concepts, you should absolutely start with SoundDevice. But here is the golden rule, the one takeaway you cannot forget. No matter which I/O library you choose, NumPy and potentially SciPy are essential for performing the actual DSP calculations. Your I/O library is a choice, your DSP math engine is a requirement. And this brilliantly illustrates our next point:
Section 4. Pi Audio Code in Action.
Let's see exactly how these theoretical tools combine into actual working Python code. When you sit down to write this, the very first thing you do is bring in your manual transmission for moving the sound, PyAudio, and your mathematical heavyweight for crunching the numbers, NumPy. They are imported right at the very beginning, working in tandem.
Let's step backward through the logic here so we can truly grasp how that raw microphone data flows. First, we initialize PyAudio and define our constants, crucially, our chunk size and our sample rate. This is basically telling the system how much audio to grab at once and at what quality. Second, we open the audio stream, linking our Python script directly to the microphone. Finally, we hit the heartbeat of the application, the while true loop. This infinite loop constantly reads a chunk of raw data from the stream and immediately uses a function like np.fromBuffer to convert that raw data into a NumPy array. And right there, inside that loop, is where you apply your DSP algorithms to the array. That is the exact moment the magic happens.
Which brings us to our final stop. Section 5. Critical Performance Considerations. Okay, before you run off to build the next great audio app, we have a serious warning. We have to look at a few things that will dictate the absolute success or total failure of your application. Real-time audio is entirely unforgiving. The crucial point is understanding these three big gotchas. First up, latency. Remember our enemy from the beginning? Real-time processing is highly sensitive to it. You must choose appropriate buffer sizes. If your buffer is too large, the user hears a super distracting delay. Second, real-time constraints. This one is huge. If you set your buffer to hold 10 milliseconds of audio, your DSP math must finish calculating in less than 10 milliseconds. If it takes 11 milliseconds to process a 10 millisecond chunk, your system falls behind. What happens then? You get awful audio stuttering, clicks, pops, and painful lag. It is just a miserable listening experience. Third, audio backends. Your operating system handles audio differently depending on the backend you're utilizing, such as Wasapi on Windows or Core Audio on Mac. So, what does this all mean? It leads us to a vital, provocative question to end on. Is your system's audio backend secretly sabotaging your DSP performance? Think about it. You could write the most beautifully optimized NumPy algorithm in the world, but if you're routing it through a sluggish, high-latency audio driver on your operating system, your real-time app is still going to stutter and fail. No way around it. I highly encourage you to look under the hood of your own operating system. Research ASIO, WASP, or ELSA. Really understand how your machine actually talks to its microphone. Because that knowledge, combined with the Python tools we explored today, will make you an unstoppable force in audio programming. Thank you so much for joining me in this explainer. Keep experimenting, keep building, and I will see you next time.